got a pretty full house here, so we're going to get started. So in this particular example here, what we've got is a typical high lift pumping station. And so we've got our high lift pump pumping from point A, which would be your reservoir, and it's pumping up, sorry, I should say point A could be something like Okanagan Lake, your source of your water, or your treated water that's ready to be discharged, just like at Poplar Point. And then point B is going to be your reservoir, like such as on top of Knox Mountain. So we've got our centrifugal pump that's got to provide the energy to get the water from point A to point B. It's also got to add velocity head to the water, and it's got to overcome any head losses. Okay, so what I'm going to do now is I'm going to switch to the other screen so that I can write on it. So when we look at this particular scenario, we have our energy at our starting point plus the head added by our pump minus any head losses that we have in our system is going to be equal to our energy at the finishing of our system. So in this particular case, what we're trying to find is how much head we need to add into our system. So if we reorganize this such that our head added be equal to our energy at point 2 minus our energy at point 1 plus our head losses. So now this is where we start defining each one of these particular scenario. So if I go back to, boy, this is going to be awkward flipping back and forth. Be patient, please, folks. So if we go back to look here, the energy, we're going to say here at point 1, so that's our energy. I guess I should have defined this as energy at A and energy at B. What can everybody tell me about the energy at point A in our system? Okay. All right, so we've got some questions came up. Basically, we've saying at this point in our system, do we have any elevation energy? The answer is no. Do we have any pressure energy? Yeah, we have atmospheric, but effectively our gauge pressure is 0. Do we have any velocity energy? And again, that's a whole lot of 0. Okay, so right now, so we're starting off at our system. We've got 0 energy at that point. Now, if we look at our finishing energy point here, do we got elevation energy? Yeah. As a couple of you said, we've got 25 meters of elevation energy. Do we have any pressure energy at that point? No, we got nothing. Do we have any velocity energy at that point? No, we've got no velocity. So all of our energy at point B is due to our elevation, and it's 25 meters of head. So now if I go back to my previous screen here, okay, which I should have written the energy at B plus, or sorry, the energy at A, pardon me, plus my head losses, plus my head added minus my head losses is equal to my energy at point B. Okay, and we reorg that to solve for our head. Our head added, which is what we're trying to figure out, is going to be equal to our energy at B minus our energy at A plus our head losses. And in our previous little discussion here, we decided that our system has 0 meters of head at the starting of it, and at the ending of it, it has 25 meters of head. Okay, so we've already figured out what our energy at B is. We figured out what our energy at A is. So now we need to figure out what our head losses are. So our head losses are going to be a function of our head losses that are major and our head losses that are minor. So if we take a look at our head losses major, that's going to be the head losses from the pipe. And we're going to use the Hazen-Williams nomograph to figure that out. Our head losses minor, that's going to be the elbows and exits and entrances. And we are going to use one of our two methods, either the resistance coefficient method or the equivalent length method, to figure out what our head losses are. So what we're going to do is we are going to figure out what our major head losses are first. Okay. Does everybody have this screen written down? Because I'm going to erase it and we're going to go do head losses major now. Okay. All right. I'm going to go going once, going twice, gone. Phew. Poof. Okay, so our head losses major are going to be a function of our pipe diameter, our flow rate, and our coefficient of roughness, and we're going to need the Hazen-Williams nomograph. So in this case, we've got an 8-inch pipe. Our flow rate, I can't remember what it was. What did I say? It was 1.1 megaliters per day. And then our C value, again, I can't remember if I switched back to my screen or not. 120, thanks, Richard. Did I get the flow rate correct? Okay, great. Now, is our flow rate in units that we can use? Nope. So we need to get this flow rate into cubic meters per second so that we can use the nomograph. So if we have Q 1.1 megaliters per day, 1 megaliter is equal to 1 times 10 to the 6 liters. And then 1 times 10 to the 3 liters, to 3, is equal to 1 cubic meter. And then 1 day is equal to 24 hour times by 1 hour is equal to, I think, 3,600 seconds. Whew. Does that seem right, folks? All right, so we get a flow rate. Then I'm going to need some confirmation in cubic meters per second from the team here. Okay, it seems like the winningest number so far has been 0.01 cubic meters per second. Okay, I'm getting lots of confirmation. Awesome. So now we've got this in our cubic meters per second. So it looks like lots of people are agreeing with that. So now we can use our information. So this 0.01 CMS. So we can use this information and our Hayes and Williams nomograph, and just, can you all just curiosity tell me what the velocity is? But I would also like you to tell me what the slope of the hydraulic grade line is. And that's going to be in meters per 1,000 meter, and our velocity is going to be in meters per second. So whenever you're ready to start throwing stuff in the chat. No, Stephanie, you don't need to convert the diameter. You can just use the 8 inches. So you'd be connecting the 8 inches and the flow rate of 0.01 cubic meters per second on the QDV line. You'd use the QDV line to tell me what your velocity is. And then you take your pivot point and your C equals 120, and you read off a slope. Okay, so Jim is throwing down 0.7 meters per 1,000 meters. And Megan's throwing up 0.3 meters per second. Looks like Gemma's, okay, Josh is saying 0.7. 0.3 meters, 0.7 slope. Okay. Just gonna wait for Francine, 0.3 meters per second, Ryder, 0.3 meters per second. Okay, looks like we're getting quite a bit of confirmation that these particular Kayla 0.3. So it looks like we've got 0.3 meters per second as our velocity, and our slope is 0.7 meters per 1,000 meters. All right, so now the thing we've got, we needed to get our slope because we know that our head losses are equal to our slope times the length of our pipe. So in this case, we have 0.7 meters for 1,000 meters times by the length of this particular pipe, which, can someone tell me what the length of the pipe is? It's because I can't switch, I don't want to switch out of the screen. 120 meters, thank you very much, Taylor. And so you do the multiplication. Because we don't have to convert the pipe diameter, because it doesn't matter which side of the, which side of the diameter line you're reading off, it's still the same side. Yes, okay, I'm going back to Josh's comment there, and yes, you have to cross the pivot line in order to find your velocity. So the QDV line connects the flow rate, the diameter, the pivot, and the velocity. Then your other line connects the pivot and the C value and the slope. All right, so it's looking like for head losses, we are getting approximately 0.08 meters of head loss. Awesome. Whew. Okay. So now we need to do the same process for the minor losses. Okay, so does everybody have the screen written down, or you need me to wait another minute here? Okay. All right. And I really am, I'm very happy that you guys are responding to me. This couldn't happen without you all participating. So thank you very much. Okay, so I'm going to erase this and we're going to go back in and look at this again. So our head added. I'm glad you think it's fun, is equal to our energy at B minus our energy at A plus losses. And in this case, our head losses major is equal to 0.08 meters. Our energy at B is 25 meters. Our energy at A is equal to 0 meters. All right, so now we need to find our minor losses. So when we take a look at our minor losses, we've got a few different things happening here. We've got some elbows and some entrances and some exits. So if we look at, what do you guys want to do? The elbows or the entrances and exits? Okay, we're getting elbows. Elbows seem to be the going. Okay, so elbows. So we've got two standard 45-degree elbows. The first thing we're going to check is, can we use the resistance coefficient method? And if we can use that method, let's use that method. Oh, I also should write down the velocity up here. Our velocity was 0.0, or it was 0.7, right? Meters per second. Oh, 0.3? Okay, sorry. 0.3. Okay. All right, can you all check in your chart for the resistant coefficient K values? Do we have a K value for a 45-degree elbow that we can use? Oh, yay. So Steph and Richard and a few more people have popped in, and that they say there's a K value for 45 standard degree elbows of 0.22. So if we look at our head losses are going to be equal to our K value times V squared over 2G. Yay, so this is easy math. So we really like this. We know our velocity already because we figured that out in our previous use of the Hayes and Williams nomograph. So we can plug everything in. Oh, can I explain why K values don't have units? Because K values basically represent a portion of, if you can think about it, kinetic energy causes head losses, okay? And what someone has done is they've gone and figured out that if you have this much velocity flowing through this type of fixture, this percentage of that overall kinetic energy will become head losses. Okay, so if you think of your K value as a percentage, that's kind of a good way to think about it. So in this case, our head loss is going to be equal to 0.22 times our velocity, which is 0.3, We got to square that over 2 times 9.81. And we end up with, okay, something really super tiny. Okay, Gemma's throwing out 3.4 times 10 to the minus 3. And I'm going to say, what's your units? Right, always meters for head losses and head added. Now we have 2 elbows, right? So we've got to times this by 2 because we have 2 elbows. So our head losses for our elbows, I'm just going to denote that with an E, is going to be equal to 6.8 times 10 to the minus 3 meters. Does everybody like that number? Well, looks like we're having some. All right, so people are saying at this point, whoa, back up, folks. Okay, so 1 times 10 to the minus 3. Okay, all right, so we're gonna just, seems like this number people aren't loving. Oh, that's okay, Gemma. That's why we're all in this together. So does everybody like this number better then? Okay. Good, I'm glad. Thanks for piping up, everybody. So again, we're still gonna times that by 2. And so we're gonna now be 2. That's a really ugly looking 2. Holy moly. Okay, 2 times 10 to the minus 3 meters. All right, so how does everybody feel about this number now? Okay, no sassing people in class, Quinn. All right, so now we've got the head losses for our elbow. And then the next thing we need to do is we need to take a look at what our head losses are for our pipe, where the water flows into our pipe. Okay, so what kind of pipe shape do we have for that one? And I might have to flip back screens to get there from here. Does everybody have this one written down? Okay, good. Okay, I'm going back into the thing just because I need to look at my dealio again. All right, so here we go. Basically, we've got the suction line has a square edged outlet and 2, oh geez, it says long radius 90-degree elbows. Oh no, sorry. Haha, never mind. So we just did these 2 elbows here. And that's it. And so we've still got to do the discharge here, and we've got a square edged outlet on the suction side, which is located down here. And we've got 2 90-degree elbows. So we've got elbow and elbow. So why don't we finish the discharge line by calculating the K value for the discharge inlet next. Okay. So we are going to do that. So I'm going to go back into, so we've done this one and we've done this one, and now we've got to do the actually outlet here. I wish I could show two screens at one time. That would be really helpful. All right. So right now, if you can imagine it, for our discharge line, it's come in and it's gone through the 45-degree elbow, and then it's popping the water out into the tank. Okay. So I want everybody, for this one, we're going to use the coefficient method again and discharge outlet, and it's going to be times b squared over 2g. And can you look up what the K value is? It actually should be 1. Anytime that you're discharging water out of a pipe, regardless of the shape, K value is always 1. And again, we've got the same velocity, which is 0.3 squared over 2g. Oh, sorry. I guess I should be head losses. It's in the same table, but I think I actually said it in one of the slides. So I'm just going to rewrite this because, boy, my writing sucks there. My head losses for my outlet, K is equal to 1 times by 0.3 squared over 2 times 9.81. Yes, and Richards, and this is for any pipe of any size diameter. And Richard is right. The outlet has entrance losses because the water is entering the reservoir. It's in the note package. So Mike, you've got it reversed. I know it's super confusing. I didn't invent this. You're just going to have to wrap your head around it some way or another. Which is why I highlighted it last class when we were talking about this. It is confusing, the wording. Okay, so Brady threw out a number of the head losses for the outlet of the pipe, which has entrance losses because the water is entering the pipe. Carly just threw out 0.005 5 meters. Does anybody want to confirm this? Okay, we're getting a yes from a few people. Fantastic. Okay. So the next step that we need to do, we've now done the discharge side of the pipe. We need to go back and do the suction side of the pipe. You've got that correct, Rich. So if we look at the suction side of the line, it has a square-edged outlet. So that means the water is leaving out of the reservoir, and it has two long radius 90-degree elbows. Now, you'll notice that this side, we haven't done the head losses in this pipe yet. It's a different diameter and it will have a different velocity. Okay, so we will have to treat this as its own separate pipe. Oh, sorry about that, folks. That was a little exciting. So now we're going to do the discharge or the suction side of the pipe. So I'm going to erase what I've got going on here. And we're going to do our major losses for our discharge or our suction side. Pardon me, I keep saying discharge. And again, we're going to go back and do the major losses. And it's going to be dependent on our diameter, which in this case is 10 inches. It's going to be dependent on our flow rate, which hasn't changed, which was the 1.1 megaliters per day, which is equal to 0.01 cubic meters per second. And our C value is still 120. And so using that, we are going to find, and the Hazen-Williams nomograph, you're going to find the velocity, and you're going to find the slope. And then once we found the slope, we're going to figure out what the major losses are going to be. Is going to be the slope times the length of this particular pipe. And this pipe is 3 meters long. Thank you, Megan. 0.2 meters per second. And 0.35 meters per 1,000 meters. How does everybody feel about those particular numbers? I need a few thumbs up or thumbs down when you get a chance, folks. Okay. It seems like some people are getting closer to 0.25 for the slope. Okay. Gemma, your velocity seems out compared to everyone else. Are you reading it off the correct line? You should be reading it off the same line where you do your QD line, where you're connecting these two. Oh, is that feet per second that Gemma's read off? Okay. Well, it seems like we've gotten a pretty good consensus that the velocity is 0.2 and the slope is 0.25. So 0.25, and that's meters per 1,000 meters times by 3 meters. And so our major losses for our suction pipe are going to be equal to something pretty little. Whew, that is small. 7.5 times 10 to the minus 4 seems to be the number that people are throwing out. Can I have a few more thumbs up or just confirmation that everybody likes that number? Awesome. Great. Okay, so those are our major losses for our suction pipe. So now let's figure out what our exit losses are. So as the water exits the reservoir, it goes into the pipe. And so we need to do the minor losses for that. So I'm going to clear my screen here. And we're going to do our exit losses. Head losses. And so this is for water leaving the reservoir. Wow. Bad. It's hard to write on a screen, folks. And again, we're going to use the resistance coefficient method. So our head loss is going to be equals K times V squared over 2G. So you're going to look up your K value for your particular type of pipe shape. Okay, so K equals 0.5. So this says, it's really bad writing, water leaving the reservoir. Whew. So basically we have our reservoir here. We've got our pipe. It's got a hole in the end. It's going up and into our pump. So the water is leaving the reservoir and going into our pipe. So according to the shape here, we've got I think it's a square edged shape to our pipe. So we look that up. Okay. And again, our head loss is then just going to be 0.5 times our velocity, which I think everybody said was, what was it, 0.2 meters per second squared, divided by 2 times 9.81. Stuart, yes, the exam will have this many parts to it. So you are going to just have to know that you're going to have to calculate the minor losses for all of the minor losses components. You're going to have to calculate the major losses for each pipe that you have. And then if that's part of a larger question like this, where I'm asking you what head added requirements are for your pump, you're going to have to put it in the energy equation. So yes. Now, I probably won't give you quite as many minor loss components to figure the head losses of, but you're going to have to, it's the same process. And I'm going to say that this question, I put lots of this in because I just wanted to practice it. Okay. All right, so I'm looking that Brady and a few other people say that they got head losses of 1.0 times 10 to the minus 3 meters. Okay. And Quinn, your question is, what is this K value for? It's for a square edged outlet, pipe outlet. All right, so now we've done this for this where the water is going into the pumping system. Now we have to do the same thing for the 90-degree elbows. So head losses for the elbows. And in this case, we've got two 90-degree elbows. So the K value for the elbows 0.22, so I'm getting 0.22, and again, we times it by the same velocity because it's the speed our water is moving in that particular pipe, divided by 2 times 9.81, and then we get a number, which is going to be something, and then we are going to times said number by 2 because we've got two elbows. Whew. 4.5 times 10 to the minus 3, or 4, pardon me. That's the first number. Does everybody want to agree with that? Okay, Francine says yes. Yay. Okay, and then you times it by 2 because we got two elbows. Thank you, Sherry. Awesome. So do I have some thumbs up that everybody likes this number? All right. Okay, so I'm gonna wait a minute here while everybody collects themselves, and then we're gonna go back to our original idea again. So this is just practice for what we did last section. We're looking at minor losses and major losses. Okay, I'm going to press the delete. These elbows are not exits. These elbows are just elbows. They're a 90-degree elbow. Okay, so we have two sort of calculations here. This calculation up here, the exit. And I'm sorry, this is kind of messy. And then we've got the two 90-degree elbows here and here. So I'm going to go back to our original slide for a moment here. Exits and entrances have to do where the pipe water is going into and out of a pipe. They're different from elbows. So if we go back to our original slide, which I'm going to bring up here. So when our water went into our system, it entered into the piping system down here, and our K value was equal to, I think it was 0.5. So we calculated the minor losses there. Then we calculated the minor losses of each of the elbows. And we calculated the major losses in this whole suction side of the pipe. We also calculated the minor losses in this 45-degree elbow, this 45-degree elbow. We also calculated the minor losses where the water was leaving out into our reservoir. And we calculated our major losses. So if we take a look at all of this, and I'm going to go back into the writing page, and we're going to write it out together. So our head losses, our total head losses, are a function of our major losses and our minor losses. So we had, if we look at our major losses, we had from our 10-inch pipe, we had major losses, and we had major losses from our 8-inch pipe. So those were our major losses. Plus, we had minor losses from 2 45-degree elbows, plus 2 90-degree elbows, plus where the water went in, plus where the water went out. So basically, if we take a look at that, we would have sort of 6 total overall losses. How does everybody feel about this idea? So what you all are going to do right now is you are going to add up all of those individual losses that we just calculated right now. It is a lot of work, isn't it? But I would ask you, Richard, to extrapolate this number to when you're pumping to a reservoir that is located kilometers away and has to go through a variety of bends and turns in order to get there. All right. Does anybody want to confirm? Oh, good question, Sawyer. So out in the real world, you're going to use design software to do all this calculations. And I know you're going to be saying there, oh, but why are you making me do this, Allison? Because you need to know what's happening in the background of all of those computer programs. Because otherwise, if you're ignorant of the actual science that goes on behind it, you can't understand where things go wrong when you're using the software. So there's a variety of different free softwares. There's some really expensive softwares. So those are, Josh, those are the head losses for the entrance and exit losses. No, this is not per 1,000 meters. This is just total head losses, Stuart. All right. So what we're going to do next is we're going to go back to our original formula. So I'm just going to delete this right now. And if we go back to our energy at point A plus our head added minus our head losses is equal to our energy at point B. And we were trying to figure out what our head added was. So in this case, our head added is our energy at point B minus our energy at point A plus our head losses. So we need to add 25 meters of head as our energy at point B. Our head at point A is 0 plus our head losses. And so our total head would be 25. Our pump would need to add this much energy. Oh, sorry. Thank you. Now, our head losses have been quite low for this particular example because our pipe is so short and our velocities are so low. But if our velocities were higher and our pipe was longer, these numbers can get quite high if you have more pipe and higher velocities. Okay. All right, folks, if someone can help Megan out with that, but we're kind of at the end of our session here. So we've done our 50 minutes again. So next week, I am going to be doing the same sort of idea where we're going to have extra lecture time since we're not doing labs. So just be prepared for that. So it's going to probably be a similar format to today. But I will have a demonstration of pump curves that I will have online and ready for you guys to go at 1 p.m. today. Is there any last questions before I check out? Yes, Erin, that's going to be on Collaborate for sure. Okay, and also if you all can, oh, thanks, Francine, that's really helpful. If you all can, if you're having any problems that you want to talk to me offline about, can you just email me?